Hi there, in this video we are going to explore the transformations of alkynes. That is, we are going to have a starting material and then we are going to convert it into various functional groups or other products of choice. So what we need to do is to figure out what kind of strategies we can employ in order to achieve the specific synthesis. So let us start from a case where we need to install the halogen in a more substituted position. Now this process involves Markovnikov addition. So what we need is an HCl, which is going to install hydrogen in the less substituted carbon and then the halogen in the more substituted position. In this other case, we have the halogen in the less substituted position. So therefore, this is going to be anti-Markovnikov addition. So we use HCl, and this requires addition of a peroxide. In the next one, we have two halide groups attached to the more substituted position. Again, this is going to be a Markovnikov addition, but in this case, we need excess of the hydrohalogen. We can also be able to revert this dihalide back to the alkyne. Now, what I want you to visualize is that we do have the protons attached to the carbon, which you usually don't show. Okay, so if we have a base, then the base can be able to do an E2 reaction where we kick out the leaving group. So if we do that twice, we're going to end up with an alkyne. The base that is appropriate for this kind of reaction is sodium amide, but we need excess of that. Okay. Now keep in mind that once we do that, we are going to form an alkyne with a proton in the terminal position having a pKa of approximately 25. The conjugate acid of the base that we are using is going to be ammonia with a pKa of approximately 38, which implies that if we have the amide, there's no way we are going to have this proton having a pKa of 25 existing in that format. So the alkyne is going to be deprotonated. So to do that and make sure that we get the alkyne in protonated form, we need to add a solvent whose pKa is lower so that it can protonate both the base and the alkyne which is deprotonated. So usually addition of water helps to achieve that process. In the next one, we have 1 mole of bromine, so that is halogenation. And the one that follows has all the positions halogenated, so it involves the use of excess halogen. The one that follows is the formation of an aldehyde. This reaction transforms the alkyne such that it installs a carbonyl in the less substituted position. What I want you to understand here is that we can install a hydroxyl group by doing hydration of an alkyne and transform it in a way that installs the OH in a less substituted position. Once we do that, the compound undergoes a process called tautomerism. The tautomerism in this process involves a base catalysis. So the base does the proton transfer, then we create a formal negative charge, and then we do another proton transfer to generate the product. So this reaction is similar to hydroboration oxidation, which we learned in the previous chapter. So it's going to involve a mild base, but in this case we need 9BBN followed by oxidation to give us the product. The next one involves the formation of vinyl alcohol where the hydroxyl group is in the more substituted position. So that is going to be similar to acid catalyzed hydration. Once we form this compound, it's also going to undergo tautomerism. And in this case, it forms a ketone. So the process here requires acid catalysis, but when we use an alkyne to transform it into a ketone, the process is usually slower. So addition of mercury sulfate makes the process to go faster. And once we form the vinyl alcohol, the process is favored by acid catalysis. So we have the proton transfer, which creates the formal positive charge there. That charge is stabilized by the lone pairs from the oxygen, and then we do another proton transfer to yield the product. In the next step, we have 1, 2, 3. So the alkyne has been cleaved. So we call this oxidative cleavage. And this reaction involves the use of ozone followed by water to form carboxylic acid and carbon dioxide for this specific one. Moving to the other end, we have transformed the 4-membered carbon into 1, 2, 3, 4, 5, 6-membered carbon. So we have created 2 extra carbon bonds. That means we have formed a new carbon-carbon bond so as to form the internal alkyne. The internal alkyne is one which is surrounded by carbon atoms. It's not in the periphery, so we call this an internal alkyne. Okay, so here what we need to do is to think of how to connect the carbon-carbon bond. So we have a bond between carbon 4 and 5. In carbon 4, we know that there is a hydrogen. Okay, so if we can deprotonate that position, we would get a nucleophile. Okay, so with the presence of, say, an ethyl iodide, we can have a nucleophilic attack in an SN2 format to create a new carbon-carbon bond. So once we figure out the appropriate base to use to remove that proton, that base must have a pKa for its conjugate acid being higher than the pKa of this proton, which is 25. The appropriate base to use is sodium amide, and then we follow that with ethyl iodide to give us the product. The terminal alkyne can be converted into an alkane if we use hydrogen and platinum or palladium or nickel catalyst, which will reduce this compound directly into an alkane. If we want to form a trans alkene, then we need to find a way to stop the synthesis at the alkene. In this case, the reagent that works well is a dissolving metal reaction, which involves the use of ammonia liquid together with sodium. We can also transform it into the cis alkene. Now to do that, we can use Lindlar's catalyst. This process catalyzes the formation of the alkene, but not the formation of the alkane. Now, once we form the alkene here, we can transform it into an epoxide. An epoxide is a three-membered ring where one of the atoms is an oxygen and two of them are carbon atoms. So we can do that using a peroxy acid such as MCPBA, which we learned in the previous chapter. Once we do epoxidation, we can transform the epoxide into a diol by using water, but because water is not a strong nucleophile, we need the oxygen to be protonated. So an acid, that is water in the presence of an acid, can be able to help us achieve the diol formation. Another synthesis we could do is to cleave the double bond which is formed over there. So we can do oxidative cleavage using ozone. So we can use O3 followed by DMS to give us 2 moles of the aldehyde. Okay, so if you look at these transformations we have done, what is involved in the synthesis of a compound requires the application of these concepts. So assuming I ask you to synthesize this compound, that is the diol, beginning from the starting material, you should be able to find your way from the starting material up to the product. So in this case, it's going to involve a number of steps. So like the first step is going to be using an amide and installing the 2 carbon atoms. And then we have another step here using a Lindlar's catalyst to give us the cis alkene. And then we can do epoxidation in the 4th step. And then we use water as a nucleophile to open the ring, and then we end up with the product.